We're starting chapter 21, which is continuing to talk about hypothesis tests. We're going to look at our null hypothesis and our alternative hypothesis. Null hypotheses have special requirements. The null must be a statement about the value of a parameter for a model. So it must be that it's equal to this parameter for the current model. We use this value to compute the probability that the observed value would occur. This probability is our p-value, which is the probability that our sample proportion would occur based on our null hypothesis being true. The null hypothesis arises directly from the context of the problem. We want to think about the why of the situation. And it's also important to remember that the null hypothesis cannot be proven. We actually use the alternative hypothesis to show what we want to prove. So the null hypothesis can only be rejected or retained. And if it's retained, we say we fail to reject it. We can't prove that it's actually true. We just prove that we either do or don't have enough evidence to keep it. The null hypothesis ends up allowing us to calculate a p-value. The p-value tells us the probability of getting results as unusual as the observed statistic. This is always given that the null hypothesis is true. The p-value is not the probability that the null hypothesis is actually true. It is the probability that the observed statistic would occur given the null hypothesis is true. We're always working under the assumption that the null hypothesis is true until our p-value tells us otherwise. The lower the p-value, the more confident we feel about our decision to reject the null, but that doesn't mean that the null is more false if you have a p-value of 1% or if you have a p-value of 6%. For example, therapeutic touch, which is abbreviated TT, is a therapy in which the practitioner moves her hands near, not touching, just near a patient in an attempt to manipulate a human energy field. This is actually true. People think this works. In 1998, for a science fair project, a 9-year-old girl tested 15 therapeutic touch practitioners to detect whether her unseen hand was hovering over their right hand or left hand. So in other words, what she did is she took one of the giant cardboard cutouts and cut places to put hands in. So they would put their hands through, and then this little girl would hold her hand, not touching the person, just above their hand. And then these people had to decide whether her hand was above the right hand or the left hand. Out of 150 trials, so she did it 10 times with each person, the therapeutic touch practitioners were successful 70 times. That's a success rate of 46.7%. What we want to know, is there evidence from this experiment that therapeutic touch practitioners can successfully detect a human energy field? We're going to go ahead and assume that all assumptions and conditions have been met, which means that we don't need to check them. Bonus. Because they're guessing whether it's over the right or the left, so they have two options, they should have a 50-50 chance of getting it right, even if they're just guessing. So our null hypothesis is p equals 0.5. So they should get it right 50% of the time. Our alternative hypothesis then, because we're trying to see if that therapeutic touch practitioners can actually successfully detect a human energy field, then they should be able to get it correct more than 50% of the time. So our alternative would be greater than 50% of the time. Because we were told that the assumptions and conditions are already met, we don't have to go check them, so we can go right into the mechanics and calculate our z-score and p-value. So to calculate the z-score, I have our sample proportion, which is 0.467, minus our null hypothesis of 0.5, divided by the standard deviation. So in this case, the standard deviation is 0.5 times 0.5 over our sample size of 150, and that ends up equaling a negative 0.808. Once we have our z-score, we can then calculate our p-value. So our p-value ends up equaling 0.788. Now, this is an extremely high p-value. that means that we're going to end up failing to reject our null hypothesis. But I want to focus on what a p-value actually means first. So focusing on what the p-value means, the p-value says if the true proportion of successful detections of a human energy field is 50%, then an observed proportion of 46.7% would occur at random about 78.8% of the time. So what this means, what this is saying, is that if the null hypothesis is true, so if they can detect a human energy field 50% of the time, then they will get it right 46.7% of the time. That will happen at random due to natural sampling variability 78.8% of the time. So that happens more than 3/4 of the time. Therefore, we're not really surprised that if they are just guessing, that they would get it right 46.7%, which means we're not surprised. Therefore, our conclusion is that with a high p-value of 78.8%, we fail to reject the null hypothesis. There is insufficient evidence to conclude that the therapeutic touch practitioners can perform better than just guessing. So again, our conclusion always states our p-value, always states whether we reject or fail to reject, and we put what it means in context. For the previous example, a 90% confidence interval would be from 0.404 to 0.536, or in other words, from 40.4% to 53.6%. In this case, we could not reject the null hypothesis, because our null hypothesis was that the true proportion would be 50%. That proportion is in the interval. So because it's within the interval, we're saying that that value could be true. Therefore, we have to fail to reject the null hypothesis. You can always approximate a hypothesis test by examining the confidence interval. The hypothesis test will give us a better conclusion or more evidence, but if you have the interval already, you can always just kind of use that to determine what your conclusion would be. All you have to do is check if the null value is within the interval. If it is within the interval, then that value could be true, which means we fail to reject our null hypothesis. If that value is outside of the interval, then that value wouldn't be true, so we would reject it. So again, if it is within the interval, you cannot reject the null hypothesis. If it is not in the interval, you can reject the null hypothesis. Up until now, when we've been dealing with our p-values, we haven't really decided what constitutes a high p-value and what constitutes a low p-value. Alpha levels are going to do that for us. Sometimes we need to make a firm decision about whether or not to reject the null hypothesis. It can't really be a, well, it seems kind of low, but maybe it's high situation. Sometimes we need to say, nope, it is below this value, therefore it's low. Or nope, it's above this value, and therefore it's high. When the p-value is small, it tells us that the data are rare given the null hypothesis. But again, what constitutes a small value? We can arbitrarily set a threshold for our p-value. If our p-value falls below that point, we would reject the null hypothesis. If it's above it, we would fail to reject. We call this threshold the alpha level, and it's the Greek letter alpha, which kind of looks like an A. Common alpha levels are 10%, 5%, and 1%. You have the option to consider your alpha level carefully and choose an appropriate one for the situation. And your context will kind of decide whether you should use 1, 5, or 10%. For example, if you are assessing the safety of airbags, you'll want a low alpha level of 1%. You want to make absolutely sure that that airbag is safe. If you're wondering if people prefer pepperoni on their pizza or not, you could probably be okay with 10% because if you're off, not really the end of the world. A lot of the times it's really hard to justify the choice, so we often just kind of split the difference and go with 5%. So most of the time that's what you will see. When we reject the null hypothesis, it is considered to be statistically significant. And that's only when we reject it. If we fail to reject, then the results are not statistically significant. Again, the idea behind this is that if we're rejecting the null hypothesis, we're saying that the current model we have doesn't work, which is kind of a big deal. so therefore it's statistically significant. If the results are statistically significant, that doesn't mean that the change is necessarily significant, but just that the results are. The alpha level, because of this, is also called the significance level. When we reject the null hypothesis, we say the test is significant at that level. So if you have a 5% significance level, or your alpha level is 5%, we say that the test is significant at 5%. The important thing here, though, is that you have to choose the alpha level before you find your p-value. Otherwise, you can manipulate it so that you will either reject or fail to reject based on what you are trying to prove. So what do we not say about significance? What do we mean when we say a test is statistically significant? All we mean is that our p-value is lower than our alpha level. That's it. Confidence intervals are naturally two-sided. Therefore, they correspond to a two-sided test. In other words, your alternative is not equal to. We can always determine what alpha level to use based off of a confidence interval. For a two-sided test, your alpha level is just 100% minus your confidence level. So if you had a 95% confidence interval and you knew that you were doing a two-sided test, you would just take 100 minus 95, and your alpha level is 5%. If you have a one-sided hypothesis test, meaning that your alternative is either strictly greater than or strictly less than, then you take half of that difference. So 1/2 times 100 minus your confidence level. So again, if you had a 95% confidence interval and it's a one-sided hypothesis test, your alpha level would be half of 100 minus 95. So in that case, it would be half of 5%, which would be 2.5%. Even though the most common are 1, 5, and 10, it does not mean that we can't use a different alpha level. It just means that those are the most common. So using a 2.5% significance level is entirely acceptable. Note, I interchange significance level for alpha level because they are the same thing. For example, wearing your seatbelt. In Massachusetts, in 2001, 51% used seatbelts. This increased to 62% in 2003. They have a goal of 80% by 2005. In 2005, they stopped 134 drivers, and 23 received a ticket for not wearing their seatbelt. Does this provide evidence that the goal of over 80% compliance was met? We want to use a 90% confidence interval with this test. This means that they want us to do a test and then give an interval in addition to the test. Again, they told us to assume that all assumptions and conditions have been met. So again, we don't have to do that. So again, bonus. For this particular example, we're not actually going to do the test or the confidence interval, but I am going to explain that in this case, because our alternative would be greater than 80, because they want over 80%, we have a one-sided alternative. With a 90% confidence, we would do 100 minus 90, which is 10. Since it's one-sided, we would cut that in half, which gives us 5%. So in this particular scenario, we would use a 5% significance level. That is all I have for today. So I will see you guys tomorrow. Have a great night.